Okay, so having seen the notion of function and related notions, let us now start solving the exercises. So here in the beginning we have 6 of them, where in each one we are given a function. We have to find its domain and range, and domain in this case means natural domain, that is the largest possible subset of the set of real numbers that can be the domain of the given function. So let's see the first one. Since so here in the first one the function is 1 plus x square, where you can clearly see that you can in fact put any real number x here in this formula. Is real the domain is the entire set of real numbers. Okay, now what about the range? The range consists of all the outputs. So we have to now figure out what the outputs can be. That we can see by looking at the formula. These are the outputs, okay, as x varies over the domain, that is in this case the entire set of real numbers. For any x belonging to the domain which is R, f of x equal to 1 plus x square. Since x square is non-negative, so 1 plus x square is greater than or equal to 1. It will be equal to 1 only when x is 0. For other values of x, whether positive or negative, this will always be strictly greater than 1. So from here what do we see? We see that the output is greater than or equal to 1. So that means this belongs to this ray, okay, and hence now this f of x is any element in the range. So the range of f is contained in this closed ray 1, infinity. Now we want to show that it's actually equal to this. For that we have to prove the reverse inclusion. So let y be an element in this set. Okay, now we want to show that y belongs to the range. That means y should be the output for some input, which means that there should be some x in R such that y is equal to f of x, which is 1 plus x square. This means now if you solve for x from this equation, then you will get y minus 1. Now from here we get the fact that x is plus or minus square root of y minus 1. Note that things make sense because y is here, and so y is greater than or equal to 1. So this y minus 1 is a non-negative real number. So, and being a non-negative real number, it has a square root. In fact, when it is positive, it has two different square roots. One of them is positive and the other is negative. So one of them is enough for us. So we now, having taken this y here in this set, we now write next this. Then this belongs to R, which is the domain. The reason this belongs to R is that y is greater than or equal to 1, such that f of square root of y minus 1 is equal to 1 plus this square. This is y minus 1. Again, when we cancel square root and square, we have y minus 1 and not 1 minus I, because y is greater than or equal to 1. So this is equal to y. This shows that y belongs to the range of f. Hence, this closed ray is also contained in the range of f. Now we can make use of these two inclusions and conclude that the range of f is equal to this closed ray. In most of this type of problems, while we are trying to figure out what the outputs are, or from the formula itself we see what the outputs are. So when we are trying to figure out how the outputs look, or in fact from how they look, where they lie. For example, here in this first part of trying to decide what the range is, we saw that the outputs belong to this ray. So in most of the cases, this set where the output belongs will turn out to be the range itself. Okay. Next, so in this case our domain is R and range is this closed ray. In the second one we have this function 1 minus square root of x. So because we have square root of x, the permissible values of x are the non-negative real numbers. Since is real, if and only if x is greater than or equal to 0, the domain is the set of all non-negative real numbers, which itself is a closed ray. Okay, now what about the range? Same procedure. Let x be any non-negative real number. then f of x is equal to 1 minus square root of x. So because square root of x itself is non-negative, so minus square root of x is non-positive, that is minus square root of x is less than or equal to 0. So if you add 1 on both sides of that inequality, you get this less than or equal to 1, which implies f of x belongs to this closed ray minus infinity comma 1. Hence, the range of f is contained in this closed ray. Now let y belong to this closed ray. Our aim is to find an x for which this is equal to y. So that means 1 minus y should be equal to square root of x. So x should be equal to 1 minus y whole square. Okay. So we can write after this, then 1 minus y whole square belongs to the domain. Does it really belong to the domain? We have to make sure that that is the case. You see, this is a square of some real number, so it will be non-negative. So it actually belongs to this, the set of non-negative real numbers. Such that f of this is equal to 1 minus square root of 1 minus y whole square. Now again, when we cancel square root and square, we have to make sure that the thing we have inside is non-negative. Our choice tells us that because we are choosing y here, so y is less than or equal to 1. That means 1 minus y is actually non-negative. So this thing is equal to 1 minus y and not y minus 1. And that's why this is equal to y. So this implies y belongs to the range of f, and hence this closed ray is also contained in the range of f. We thus have range of f equal to, in this case, this interval. Then number 3, here the function is f of t equal to 1 divided by square root of t. Because of the presence of square root, again we cannot take negative values of t, but at the same time, since this term square root of t appears in the denominator, so it cannot be 0 also. So only positive t's are allowed. Since this is real, if and only if t is positive, the domain in this case is this open ray, not like this one. This contains 0, this does not contain 0. Okay, now next let t be any element in the domain, then f of t, which is 1 over square root of t, is also greater than 0. And so f of t belongs to 0, infinity. Thus, the range of f is contained in this open ray 0, infinity, and our guess is that it's actually equal to this. So now we have to prove the reverse inclusion. So let's proceed for that. This is only a guess. Okay, when you guess something like this, before proving it, you don't really know that your guess is correct. Maybe some gut feeling is telling you that this should be equal to this, but then you have to prove, and then only you can write this is range is equal to this. We may be wrong in our guess. Next, let y be any element in this set. Again, like before, we want a t such that 1 over root t is equal to y, but at the same time we want a t here in the domain. So solving this equation for t gives us what? 1 over y square. So when our y is a positive real number, 1 over y square is also a positive real number. So our guess is correct, we can almost see. Then this belongs to the domain. If you want to stress the fact that these pre-images, that is y, we want y to be an output, an image, this is a pre-image of y under the function capital F. If you want to stress the fact that you are taking the pre-image inside the domain, then you also mention that this set is actually equal to the domain of F. Okay, then 1 over y squared is an element in the domain of F such that if you want to really be strict about these calculations, you can write these intermediate steps. Now 1 over y is a positive real number because y is positive, and so when you cancel square and square root, you get 1 over y and not minus 1 over y, and this is equal to y. This shows that y belongs to the range of F, and hence our interval also is contained in the range of F. Thus the range of F is this interval, which is the set of all positive real numbers. In this case, the domain and the range are the same. Then 4. Here the function is f of t equal to 1 over 1 plus square root of t. The problem with 0 that we had here, we don't have it here because the denominator is a positive real number. Whenever it is well defined, whenever the denominator is a real number, it's a positive real number. How can we say so? Because 1 is positive and square root of t is by definition a positive square root of something, namely t. Now it will depend on what t actually is. So t here is, it can be any non-negative real number because we cannot take t negative. Since 1 plus square root of t is greater than 0, if and only if, or in fact instead of writing greater than 0 we can write not equal to 0. That stresses the point. If and only if t belongs to the set of all non-negative real numbers, the domain is the set of all non-negative real numbers. Note one subtle thing here. This statement that 1 plus square root of t is not equal to 0 also includes in it the fact that 1 plus square root of t is a real number. Okay, that thing is included here. This is a real number and is not equal to 0 if and only if t belongs to this. Okay, so normally we don't write such things, but you have to understand that this quantity, this number being real, is there in the background or is included in this statement, although it's a negative statement, something not being equal to something else. So our domain is this closed ray. Okay, now for any t belonging to the domain. Again, I am saying, if you want, you can stress the fact that this set is the domain of X, just like there. We have f of t equal to but in this case the f of t, the formula is not that straightforward. So instead of directly going to f of t, we can write something else. I mean, let us first see what happens to this. 1 plus square root of t is greater than or equal to 1. Hence, f of t, which is 1 over 1 plus square root of t, is less than or equal to 1. Okay, which follows from this inequality. Also, clearly f of t is greater than 0, because this is a positive real number and non-negative real number actually. Oh no, wait, what am I saying? This is a positive real number. I was confusing 1 with 0. This is a positive real number, so its reciprocal is also a positive real number. Hence, our output belongs to this half open interval. It's greater than 0 but less than or equal to 1, which implies that the range of f is contained in this half open interval. Now, next thing is, our guess is that this itself is equal to the range. So, let y be an element in this set. We are seeking a t where here in the domain such that this is equal to y. So this little calculation in trying to figure out the pre-image such that the image of that is y under the function, you have to do it separately, and then when you get the pre-image, you just use that and solve the exercise directly. 1 plus square root of t is equal to 1 over y. But every step has to be carefully seen for error, carefully monitored. We have chosen y here, so that means y is not equal to 0. Y is a positive real number, so we can take reciprocal. Okay, so there is no problem with this step. And then one over y minus 1. This step also there is no problem. So that means t is 1 over y minus 1 whole square. since this is the square of some real number 1 over y minus 1, so this t is a non-negative real number, so it will be here in this set. So that means this is our value that will work, 1 over y minus 1 whole square. Okay, then belongs to the domain of f such that f of 1 by y minus 1 square is equal to square root of 1 over y minus 1. Always be careful when cancelling square and square root. The number that you ultimately will write has to be a non-negative real number. Okay, so it's now time to decide which one of the two possibilities it will be. Will it be 1 over y minus 1 or 1 minus 1 over y? Let's look at the place where y is coming from. Y is satisfying these inequalities, so that means 1 over y is greater than or equal to 1. Note that 1 over y makes sense because y is not equal to 0, and at the same time this inequality implies this because y is positive. So that means 1 over y minus 1 is actually non-negative. So when we cancel square and square root, we will have 1 over y minus 1. Okay. And this, if you skip one step in between, this will ultimately be equal to y. So we have shown that y appears as the output of something from the domain under the function. Thus y belongs to the range of f, and hence this, oh sorry, this is not our set, this is our set, because from here we are choosing y, so this is contained in the range of f. Hence the range of f in this case is this half open interval 0, 1. Two more are there of this type. Number 5, this time the function name is g. G of z equals square root of 4 minus z square. Note that g of z is real if and only if 4 minus z square is non-negative. But 4 minus z square is non-negative if and only if 4 is greater than or equal to z square. So you use the here we have to decide what z is by recalling those quadratic inequalities that we solved. So that means absolute value of z is less than or equal to 2. In other words, the distance of the real number z from 0 should be less than or equal to 2. So that means z should belong to this closed interval minus 2 comma 2. So in this case the domain is d of g equal to minus 2 comma 2. Next we calculate the range. Let z be in, I think I need ink. Okay, so next we let z be any element in the domain then so if z belongs to this, looking at this equivalent inequalities, we see that 4 minus z square is non-negative, then 0 is less than or equal to 4 minus z square, and so 0 is also less than or equal to g of z, which is equal to square root of 4 minus z square. But that's not all, something else is also true. This is not just non-negative, but this is less than or equal to 2. Also, z square is non-negative because it's a square, which implies 4 minus z square is less than or equal to 4, because minus z square will be non-positive. So you add 4 on both sides, you get this, and this implies, okay, now what we are now going to do, we are going to take square roots on both sides. The question is, can we do that? We can do that because 4 minus z square is a non-negative real number, so taking square root makes sense, and when we do that the inequality will remain, I should not say remain the same, but it will not change direction, it will not get reversed, and positive square root of 4 is 2, that is g of z is less than or equal to 2. So g of z besides being non-negative is also less than or equal to 2. That means it belongs to the closed interval 0, 2, and hence the range of G is contained in the closed interval 0, 2. Now we want to prove the reverse inclusion. Let y belong to this closed interval. Well, you can ask me one question. Fine, for z belonging to the domain, we see that g of z, the output, is non-negative. How do we know something else is also true? Namely, how do we guess before continuing the calculation that g of z at the same time should be less than or equal to something? To answer that, you should look at the case. I mean, it's not possible that only one strategy will work in all the problems. So you have to look at the formula. From the formula itself you will have, I mean, you can imagine what the values are going to be. From that and from your experience in working with this type of things, you will guess that something else should also be true. Or in the worst case, if from this first inequality itself you can of course say that g of z belongs to this. Suppose you it did not come to you that at the same time it will also be less than or equal to 2 or less than or equal to something. So you conclude that g of z belongs to this, so that the range of g is contained in 0, infinity. This is a true statement, there is no problem with this. But then if you try to show that this is contained in the range, then you will encounter some difficulty. At first, when you start working with these things, of course you will make such take such naive steps which will not necessarily take you directly to the answer. But then by struggling with those situations, you will gain experience, and then you will be able to guess this type of things. Okay, so next let y belong to this. Now our job is to find a z belonging to the domain so that this is equal to y. So we solve for z. 4 minus z square is equal to y square. So with respect to this, z and y are symmetric actually. You can interchange their places. Okay, now we are going to take square root again. Is that possible? That is possible because, see, we have chosen y here. So that means y is less than or equal to 2. At the same time y is greater than or equal to 0. So we can square on both sides and get y squared less than or equal to 4. There is a danger in this calculation. This in general may not be true. Let me show you why. If y is not positive, you may encounter a case like this. Say this is your y. Okay. Just saying here y is positive means y is non-negative, so there is no problem. But just to show you what can go wrong if one just simply takes this and then writes this as a consequence, then now if you square y, on this side you get 9, on that side you get 4, and this is not true. Okay, so non-negativity of y matters here. So that means we can take square root, and taking square root, of course, we will get two things, but it's enough we take the positive one. So root 4 minus y square is our pre-image. Then square root of 4 minus y square. Oh, but at the same time we should also somehow say that this thing belongs to the domain Okay, we cannot directly write this. Instead, we have to do our calculation like this. You can write directly, it won't be that clear. Then 0 is less than or equal to y, which is less than or equal to 2. That implies 0 is less than or equal to y squared, that is less than or equal to 4. That implies 4 minus y square I know what is to be written here after this, but can we get everything from here itself directly? What I am trying to say is that 4 minus y square. Okay, yes, from both the inequalities. First of all, see. From this second inequality, we get the fact that 4 minus y square is non-negative, because you can subtract y square from both the sides. From the first inequality, you get the fact that this is less than or equal to 4, because minus y square is non-positive, that means y square is non-negative, which is true. Now this implies, now we can take positive square root again, because of the same reason that just like y, 4 minus y square is non-negative. So is less than or equal to 2. Now note carefully that minus 2 is less than 0 and 0 is less than or equal to no, this is not, sorry, because of the sameness of this root 4 minus z square and root 4 minus y square, wanted to write g of z, but that's not what we are doing here. 4 minus y square is less than or equal to 2, and this implies that, yes, now we can say that this belongs to the closed interval minus 2 comma 2. Actually this will never be equal to minus 2, but that is not a problem. It is a real number here, such that we should, I think it's better, instead of writing such that, better to write and this is equal to what? 4 minus y square, its square root and square of that. Okay, now when we work inside this outer radical, we cancel square and square root. After that we write 4 minus y square. That is because 4 minus y square is non-negative, not y square minus 4, and this is equal to square root of y square. Now what will you write here, plus y or minus y? That will be determined by the sign of y. Y itself is non-negative, so we will write y. So this is our input in the domain for which y is the output. So any y here appears as the output of something under the function. This implies that y belongs to the range of g, and hence the range of range of g. Okay, fine. So that means 0 comma 2 is contained in the range of g. Now combine this with, where do we have that other thing here? Thus the range of g is this closed interval, and there is one more, 6. Now in 6 we have taken the reciprocal of what we have in 5. Here the function is 1 over square root of 4 minus z square. First of all, domain. Determination of domain is actually quite straightforward and much less complicated than the determination of the range. Note that z square is not equal to 0. Again, here it means that this is real and non-zero. If and only if we can, ideally we should again do the calculation because this is a separate exercise, but from the previous exercise calculation, we can directly write if and only if z belongs to the open interval. That is because to make this radical a real number, 4 minus z square should be non-negative, and for that we have already seen that the equivalent condition is that z belongs to the closed interval minus 2 comma 2, but minus 2 and 2 are the values for which the expression inside the radical becomes 0, and so the radical also becomes 0. So we have to remove those two values. So doing that we get this. Hence the domain is d of g equal to this open interval. Okay, next, determination of range. Let z be any element in the domain of G. Then okay, instead of taking leaps of faith, let us do the calculation. So being here means being in between minus 2 and 2 strictly, right? So now this implies okay, now z can also be negative. Oh, but we can of course conclude from this that the absolute value of z is strictly less than 2, which will imply that the absolute value square, which is nothing but z square, is less than or equal to 4, and this implies 4 minus z square is less. Oh, sorry, equality is not an option. 4 minus z square, and this implies square root of 4 minus z square is greater than 0, and hence 1 over square root of 4 minus z square, which is g of z, is greater. Did we really need to do these calculations to conclude this? Because it's obvious, no? But the question is, what else is true? Is there something else that can be said about the outputs? Are the outputs okay? There, taking our cue from the previous exercise calculations, their square root of 4 minus z square, we have already shown that it is less than or equal to 2. So will it not imply that its reciprocal is greater than or equal to 1 over 2? The reciprocal is greater than or equal to 1 over. In fact, that's what we want to prove. Then, which implies, okay, let us use previous exercise calculation once more. This implies square root of, at once we are writing this, we have already seen, we have seen that this is less than or equal to 2, but equality is not an option now because minus 2 and 2 are not values. Am I saying the things correctly? We have the calculation here, no? Instead of guessing blindly like this, let us actually once and for all let's do everything. Then, and this is not how we should approach. 0 is less than or equal to z square. This is true even for z that does not lie in this interval. This is in general true for any real number z, which implies 4 minus z square is less than or equal to 4. Okay, now this implies now we can take square root because 4 minus z square is greater than or equal to 0. Sorry for this back and forth things. I'm trying to figure out the thing. I don't have the solution itself with me. I'm just going on instinct and the things. Okay. Then just like here, so essentially we are repeating what we have here. The only thing is that now our starting point is not like this, but z now lies between minus 2 and 2, that too also strictly. So that means, okay, now I can see the path. Then minus 2 is less than z, which is less than 2, and this implies 0 is less than or equal to z, and 0 is less than or equal to z square, which is less than 4. Okay, so that will imply, first of all, four minus z square is strictly greater than 0. We have strict inequality here, and at the same time this is less than or equal to 4. Here we have strict inequality because it's coming from this, and here we have ordinary inequality because that is coming from here. Minus z square is non-positive. Now we can take square root. Taking square root, positive square root, we get this, and it continues to be true that this square root itself is also positive and it is not equal to 0, and so we can take reciprocal on both sides and finally get this, which we were seeking. Four minus z square, this will be greater than or equal to 1 over 2. Thus, g of z belongs to this closed ray 1 over 2 comma infinity, and hence the range of G is contained here. Okay. Now let Y be any number in this set, in this closed ray interval. We now want, of course we want SZ such that this is equal to Y. Four minus y square, 4 minus z square is equal to 1 over y square if we remove the square root. That means 4 minus 1 over y square is equal to z square, and so this is equal to z. Okay, so we have to say that 1 over y square is less than or equal to 4 in order to make this our pre-image, and that will come from this condition. Then this implies 1 over 4 is less than or equal to y square. Here taking square on both sides is not a problem because 1 over 2 is positive and so y is also positive. It's greater than or equal to 1 over 2, and because of that we can now take reciprocal. The inequality will get reversed, and so 4 minus 1 over y square is greater than or equal to 0. Hence we can take its square root because it's a non-negative real number, and its square root will belong to the domain. Oh, we have to say that also. Okay, fine. Square root of this will belong to the domain. For that, what should I show? We need to show this. Oh, this is not a very big problem. So we cannot directly write hence. Now okay, let me first gather the pieces. What do I need for all of this? This inequality is trivially true. For this one we need okay. Now 1 over y square is greater than or equal to 0. Note that because we are choosing y from here, so y is non-zero, so 1 over y square makes sense and it's a non-negative real number. This implies 4 minus 1 over y square is less than or equal to 4, but we have already shown that this is greater than or equal to 0, so why don't I make it a part of my calculation, and because of this now we can take square root on both sides and we get four minus 1 over y square is less than or equal to 2. This implies that is this belongs to the domain. Oh, we are writing less than or equal to 4. Something has gone wrong in this calculation. Can we have equality here? No, we cannot have, because you see 1 over y square, of course it's non-negative, but more specifically it is positive. 1 over y square is never equal to 0. So we have strict inequality here, and because of that here we have strict inequality. So here we have strict inequality here, so that's why this is less than 2. Okay, and this is the domain of G, and okay, finally we are able to calculate the value of G at this point. This is equal to this is 4 minus 1 over y square after cancellation of square root and square, because that is non-negative. And this is equal to 1 over square root of 1 over y square. This is 1 over y because recall that y belongs to this closed ray, and as such y is positive. Y, that is, y cannot be negative. That is our point. So this is equal to y. Thus y belongs to the range of G, and hence our closed ray is also contained in the range of G. Thus the range of G is equal to this closed ray. Things escalated pretty quickly from one problem to the next, but we can expect that because we start off very easy and then we move on to the more and more difficult problems. Okay, now next we come to the question of which type of curves can be graphs of functions. Exercises on that thing. In exercises 7 and 8, which of the graphs are graphs of functions of x? Give reasons for your answer. Okay, now I need to draw the things. As nicely as I can. There are two parts. Our first curve looks roughly like this, which you can guess is a parabola, not this type of parabola, but this type of parabola whose axis is parallel to the x-axis. And then in part B, we have another curve which is not which is not entirely something that has a name, but parts of it are known curves, and the curve looks like this. A part of the curve is straight line, and then a part of it is a parabola that looks like this, and another part of it is a curve that goes something like this, which looks the third part looks somewhat like the graph of this function. We don't know, and we don't really need to know exactly what type of equations correspond to this curve. Okay, so we have been asked to ascertain whether each one of these curves can be the graph of some function of x. The curve in part A is not the graph of any function of x. What is the reason for that? The reason is the vertical line test. Had it been a function, some function of x, then for some given value, for some given input, say here some x prime, the vertical line that passes through that point should have crossed the curve at exactly one point. However, you can see that for those x's for which the vertical lines through them intersect the curve somewhere, they intersect at 2 points except exactly one x where the vertical line is the tangent to the parabola. For this special x only, there is one point of intersection. So if this is the graph of some function, then at this input it will have two different outputs, which is not allowed when we are talking about functions. One of the outputs is this one, say y, and the other output is here, y prime. So x prime comma y and x prime comma y prime are both points on the curve. So at a single input we cannot have two different outputs. So this curve fails the vertical line test, and as a result it cannot be the graph of any function of x. Function of x, keep that in mind, our inputs are coming from here. As a function of y, it will be the graph of a function which you know which function it is, x equal to y square. But let's not complicate matters further. This is not the graph of a function of x. But if you apply the vertical line test here there is no problem. Here the domain will be this closed interval. The domain is the closed interval determined by these two real numbers, and at any point in the domain the vertical line passing through that point crosses the curve at exactly one point. So the uniqueness of outputs is maintained here. So this will be the graph of some function. Should we write the reason? I mean, I have said what the reason is. If you want, you can make it a part of the solution. You can write that this curve fails the vertical line test, whereas the one in part B, it satisfies the vertical line test, or it passes the test. Is the graph of some function of x. And just like that, there is another problem. I mean, the 8th one, where also we are given two such curves. For the 8th one, part A curve looks like this. This is even more messed up than the part A of 7. Here the curve that is given it looks roughly like this. So here I say it's more messed up than part A of 7 because for some inputs the vertical line passes through the curve at more than 2 points. crosses the curve at more than 2 points. So here the situation is even worse. So clearly it cannot be the graph of a function. But what about part B? Part B also is not the graph of any function. In fact, it's an ellipse. Can I draw it nicely? My drawing skills are very bad. You can understand what I am trying to draw here. It's an ellipse. So it is also not the graph of a function, because just like before, it fails the vertical line test. No need to write that much, that if you draw a line perpendicular to the x-axis passing through that point, then that line crosses the given curve at more than 1 point. You can just simply write it fails the vertical line test. So it cannot be the graph of any function of x. Okay. So after these two exercises, there are of course many more. The next set of exercises of one type asks us to find formulas for functions. So far we have seen that we are given formulas for functions. We have been asked to find the natural domain and range, and then we are given curves. We are asked to say whether the curves can be the graphs of some function. But after that, we encounter some problems where some conditions are given which a set of variables satisfies. From those conditions, we have to figure out what the formula for the function that they are talking about in that problem are. Okay, so what the formulas are, we have to find those formulas, which however we will tackle in the next video. So let me end the video here itself. So if you want to comment on these things, you are welcome to do so in the comment section, or you can mail me also here. So that will be all for today. And what is there tomorrow? Tomorrow we have analysis, because we will do that. So see you tomorrow. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.